Hi, I'm Leow Cheah Wei, and I am presenting about WebSocket versus HTTP implementation on RT-Thread. In my line of work, often I need to do Internet of Things or Industrial Internet of Things using microcontroller board like RT-Thread HMI board to connect to sensor at remote location or at machine to send data to a cloud server or the on-premise server for display, for real-time data display. So there are various methods that we can use in doing this, which I'll present later. And today we're gonna compare WebSocket versus HTTP. Which protocol is better for real-time processor sensor streaming? How do they impact the RAM, CPU, and power on the RT-Thread HMI board, which is based on Renesas RS6 M3, and the implementation trade-off for embedded system. I also put my contacts over here, LinkedIn, in case you want to contact me. Let's look at some terminology. RT-Thread is the real-time operating systems that's running on the board that I'm using today. And there are also terminology about AI models, real-time operating system, Internet of Things, IoT. In industrial IoT, it often requires a microcontroller that can provide sufficient connectivity to electronics components, and from there to the cloud system. In this sense, RT-Thread has a wealth of libraries such as MQTT, WebSocket, HTTP, that making such endeavor possible across many boards that run RT-Thread. In fact, if I want to change to another board that's supporting RT-Thread, there is not many changes that I need to make because my program can be run. This presentation focuses on WebSocket and HTTP. On the diagram here, on the photo here, you actually see an actual example system that I do for a remote terminal unit correcting RAN sensor data. You can see the RAN sensor here. And in this system, you actually have the 4G router. It has the RT-Thread HMI board. It also has some I/O to actually detect other things. So in the example just now, the optical rain sensor is correcting rain data, and from there actually give like how intense is the rain to the microcontroller. Very often in industrial type of sensor, the output is either RS485 or running the Modbus RTU, or 4 to 20 milliamp analog output, or 10 to 20 watt wattage output. So depending on what output you need to get from your microcontroller or is available from the sensor, you need to adapt it to the microcontroller. Although the HMI board, in my case, it actually have other bus like CAN bus, it doesn't really have a RS485. So I got to use an external RS485 to UART conversion to bring the signal from the optical rain sensor onto the HMI board. So in terms of system architectures, we have the sensors at the edge, the microcontroller board at the edge, HMI board. We have the cloud, and we have the command center that eventually we want to look at multiple RAN sensor at multiple locations. So this shows the connection diagram where the sensor connect to the microcontroller and is sent to the cloud. And the cloud, we normally have things like database, like Postgres, running on a cloud server, ECS, and I often use .NET as the backend as well as front end. So in this case, the HMI board, the Artitrade HMI board, contains the real-time OS that makes such program feasible. It has networking stack. It actually have Wi-Fi. It has Ethernet. Although here I'm just using the Ethernet connected to the 4G router to send to the cloud. The CPU is at 200 megahertz with 512 kilobyte of RAM and flash and 2 megabyte of flash. It actually even comes with a LCD display, touchscreen, that we can actually program to show the optical range sensor on site on the screen if we want to look at it on site. The key constraint when we deal with IoT system is on the RAM and also the real-time requirements. Often the microcontroller that we choose is of limited RAM as to save cost. As I mentioned, today we're going to compare two protocols, HTTP and Websocket. First, let's look at HTTP. This is one of the simplest and oldest older communication protocol. It uses a request-response model where it is stateless but having a little bit high overhead because each header that we send contains the header and the payload. The use case typically configuration update means, let's say we want to change the sensor acquisition rate. For example, we want to let it collect data faster or collect slower or change the IP address. So those are configuration updates. Because it's actually not very suitable for real time, so it's suitable for non-time critical telemetry. In the optical range sensing, actually is still usable. Yeah, let's look at how HTTP works. From the HMI board that's connected to the range sensor, it will actually do a request to the server through HTTP post, and the server will respond. Subsequently, the session will terminate. Next, when the HMI bot get another round of requests on range sensing, it will make another HTTP post to the server, and the server will need to respond again, and this continues to go on. That's why actually the overhead is a bit high, because we need to keep on starting and waiting for response and stopping the session, and then the process repeat again. In the WebSocket case, the connection is persistent. If you look at this diagram, first, the HMI bot still need to make a WebSocket request to the server, and when the server accepts it, the connection will stay. So as long as the connection doesn't go down, the HMI bot just need to keep on sending data to the server. The server can also send data to the HMI bot. It is actually full duplex until the connection is closed. So with this, it is lesser payload because all the data sending in between here, it doesn't need another new session to be created. And it also doesn't need to have extra header just like the HTTP just now. So the typical embedded use case is live sensor streaming. That means we want to have streaming data, and then we want to have interactive control so that the server can control the HMI bot faster. So here I highlight the key differences in terms of connection. HTTP is short-lived. You need to have start a new session again every time you send a request. But WebSocket is persistent. In terms of latency, HTTP is higher than WebSocket because it is some sort like polling. You need to keep on send and request, send, wait, request. So it's like polling. And WebSocket is, once the connection is up, is like the client, the HMI bot is just keep on pushing data to the server. So latency is low. In terms of RAM usage, per request, HTTP may be low because it will need to start that and stop again. The WebSocket might be higher. It have buffer overhead. But in my example, I actually find that sometimes WebSocket have a lower RAM usage because it doesn't need to maintain a lot of buffer for as compared to HTTP because it only once the connection is up, it doesn't need to send header again. In terms of CPU use, because the HTTP is per request, so it is like up and down, whereas the WebSocket is rather steady. So let's look at how when we want to use HTTP. On the right-hand side, I actually show some actual code for my projects. The top portion is actually an example of the HMI bot getting data from the server. So what is important here is you can see we have a web client session. Web client is the library that is used for doing HTTP on the RT thread. We create the session with some buffer size. Then after that, we do the web client get and from the session and from the URL, and we check whether it gives us a good response. So if it doesn't give a good, if we give it a response 200, we actually will say it is a connection failed. So likewise, the example below is the web client post. So that means we are posting data to the server. So again, we need to create the session. We need to create all the header. You see all this header, the content of the header is, for example, here, content type application JSON. And so these are the things that we need to send to the server each time and wait for the request. That's why HTTP, the package is higher than WebSocket. We'll see WebSocket later on. So after that, we can actually do the web client post. And again, we check whether the response is good. So HTTP is still having a low RAM system if the messages are infrequent. But if the message is frequent, like for streaming data, then the RAM usage might be even higher than WebSocket. As I find out, because my example later on is actually on the streaming data. It has a simple get post workflow. It is suitable for battery power if the sending data or polling is already happened. So this is again to summarize from these two examples. To fetch data, we use web client get. To post data, we use the web client post. Now let's look at WebSocket. When we want to deal with streaming data, that means data keep coming at higher frequency, like more than 0.5 Hertz. That means like 2 samples per second. Or we want some more interactive, more real-time control, like the server can control the user interface, the HMI. Or we have a stable power supply, as in my case just now. Actually have constant power. If I look at this, like actually have constant power. So which is a stable power source. So we find that actually the WebSocket is more suitable. So to use the WebSocket, we just need to open the connection using this command called no_poll_con new. After that, let's say we want to stream the data, we just need to do the no_poll connection send stacks to the server represented by the WS, and then our data encapsulated in a JSON format. JSON format will look something like this, and of course we need to tell the system the length. Then once we are done, we close the connection. Here are the real code that for my projects. You can see that we need to use a no_poll connection new to connect to IP address. right? WebSocket address of your server. And if the connection is failed, she will detect it. If it's okay, we just say it's okay. So once the connected established, we can start to do the no pole connection send text. So this text has to be inside a JSON. So that's why like this inside JSON. So that's why we actually construct the JSON and put items into the JSON before we send. So when everything finished, we close the connection, no pole underscore connection. Remember that we need to do a delay, like in this case, a delay for every cycle because this will keep running. Otherwise, the system might run too fast and overload and hang. So in summary, at least for streaming data, my example is actually really streaming data. But overall, WebSocket advantages have persistent connection versus HTTP that need frequent reconnect. The WebSocket keep a single TCP connection open and maintain it, and then data keeps sending. HTTP, it creates a new connection every time, although we actually can reuse it with HTTP to keep alive for each request response. Impact is the HTTP overhead is higher due to repeated handshakes and headers. WebSocket avoided this by just using the same connection. WebSocket have less header overhead. WebSocket frames are lightweight because it doesn't need to have the same header every time it sends data. HTTP request response carry heavier headers, often hundreds of bytes. Impact. Over time, WebSocket use less memory and bandwidth for frequent messages. Onboard peripheral configurations is needed to make the WebSocket use. For example, we need to enable UART. We may want to enable real-time clock so that we send the timestamp together. This can be done in the RT-Thread IDE, where it actually integrates with the Renesas FSP configuration. We call it Smart Configurator. We can configure it by invoking the FSP Smart Configurator from the IDE. Here I show the screenshot of enabling some peripherals. The IDE is also very useful when it comes to testing. We call it debugging, where in this case, once I run my program, the WebSocket meter, I actually can see all the things in the log console. And also I can also normally I also send the data to the console to the program screen command prompt. Here you can see that the output. So again, I have to say that for both HTTP and WebSocket, the data payload is put inside or encapsulated in JSON. The debugging can be done by looking at this debug console. An example of sensor readout can be observed seen here on the command prompt. So to use WebSocket or HTTP and also the associated libraries like the JSON, we need to include all those through the library package manager inside RT-Thread. Yeah, it is something like here. If you can see this screen, we need to click on the package, then we can select the package. So once we selected the package, you can see that the package is listed in your projects directory. In this case, Agile Mobus CJSON LVGL for the screen. And web clients. So web clients is for HTTP. No-pole is for WebSocket. So depending on what you want to include, use, you put the library package. Then you include the header files at the top of your program, just like this, the top. Example packages used are for data encapsulation and Modbus RTU because normally like industrial sensor, there are IS-45 over Modbus RTU. So with this, I can introduce you about Agile Modbus library that can be used for RT-thread. And CJSON is another library that is used for JSON parsing. So this is JSON, and you can actually look at the GitHub on this library, where actually, for example, if we were to use MQTT, which I actually did not compare today, we can actually put different metrics of a particular sensor in a value pair, name value pair, like T current, H current, and then dot the value, and all this encapsulated into the JSON format with the timestamp. TS is timestamp. That's why you may want to enable the real-time clock as well, if your board has that. Other useful library for IIoT, which is not used in my project today, is MQTT, popular for IoT, and firmware over the air, or called OTA. So this can be seen under this. In fact, there is a built-in example of OTA for the RT-thread HMI board. So let's see what are the possible optimization we can do for HTTP. Again, HTTP, because the session will need to be established each time, but we can optimize it by using the keep alive or reuse the TPC session. Although I did not really try it much, we can actually also compress the header with HTTP/2 so that the package becomes smaller. For WebSocket, we can tune the ping interval to balance keep alive versus power. Yeah, use binary frame, no text for sensor data is more compact. But generally, WebSocket packages are smaller and compact. For both, we can enable the RA6M3 hardware crypto TLS acceleration. So there are other cases where we have to have hybrid approach, where we actually have WebSocket as well as HTTP implemented. So for example, the boot, we use the HTTP for initial config from the server or something. And for runtime, once we start running, everything is stable, we use the WebSocket for live data. And if the WebSocket is down for some reason, it will fall back to HTTP. Yeah. So we need to write the code to do this. This gives us two possible way of using the hybrid approach. In terms of RAM saving, we can release the WebSocket buffers in fallback mode. We can do resource monitoring on RT-thread RT-thread Studio. So some of the live RA6 metrics are like HTTP mode shows the RAM CPU spike during polling. The WebSocket mode shows steady resource usage, and then hybrid mode transition between, depending on our use case. In terms of resource debugging, we can actually use some command like below, like list map. It will show the heap stage usage, critical for WebSocket buffer because it might overflow. Yeah, we want to avoid the overflow. Yeah, free, it shows how much RAM are available. Watch for leaks during long WebSocket, WSM for WebSocket connection, and CPU profiling. There's also a CPU usage that tracks CPU load during HTTP polling burst versus WebSocket steady state. Yeah, so this is how it looks like. One example, if I type PS, it will actually show the thread visualization, which thread is running and what is it doing. In network debugging, which is often happening, normally, for example, if your IP administrator doesn't allow certain signal to go through certain port, this might prevent it from working properly. So there are some tools that you typically can use, like NetStack, to compare active HTTP, multiple short-lived versus WebSocket, one persistent connections. Package sniffing, you can use package Wireshark Wireshark, for example, to analyze overhead HTTP header versus a few WebSocket frames. In power debugging, actually there are hardware to do so, but I do not have that. Yeah, but you can use the RA6 M3 PMM power management module. Measure the current draw during execution or sending data, and HTTP handshake, whether there is spike or during WebSocket either. That's come to the end of my presentations. Thank you very much. Yeah, again, just to introduce myself, I'm Leow Cheah Wei from Malaysia. I run my own company called Leow Cheah Wei. And here is my LinkedIn contact. Search for Cheah Wei on LinkedIn. Thank you.